Hi guys, so far we studied the electric currents induced in well-defined paths in conductors just like circular loops. Suppose if a magnetic flux changing when a bulk piece of conducting, so then the change in magnetic flux induces a currents around that conducting material. Now these currents are known as eddy currents. These eddy currents are also known as circular currents, which was first discovered by Foucault. Let's see these eddy currents, how they form and how they affect. As per we said, so we need a bulk piece of conducting material. So this is the first priority, bulk piece of conductor. So here in these demonstrations you are seeing the thick pieces of copper material and the magnets which are present in hand. So these magnets are strong magnets, so which is called as neodymium magnets. So this neodymium magnets are strong magnets. If the neodymium magnets is hanging, if you can see how the copper material is applying a resistance. Yeah, this eddy currents is also we call as resistance. So but that resistance which is not comes due to because of the current, it is resistance which opposes the motion. So if the magnet is dropping, you can observe the magnet slows down. So let us take a situation. So here this neodymium magnet is hanging. It's hanging and a thick copper plate. This is thick copper plate is kept under it. Suppose if this magnet, when it in motion, when it comes to interact with this copper plate, so the magnet is stopping eventually. So the motion of the magnet slows down. So how it is possible? So this neodymium magnets is strong magnets. It applies a magnetic flux. So if I draw magnetic flux, let it be the direction of magnetic flux for a momentary. So this is the direction of magnetic flux. This magnetic flux is crossing through the thick copper conducting material. We know that the change in magnetic flux causes an induced current. So induced currents will set up in these thick copper plates in a circle. So this induced current opposes the motion of the magnet by developing same pole of the magnet. So here if you can observe, if the magnet is released, so the motion of the magnet is eventually slows down. So how it is slowing down? So here there is no interaction, so there is no friction, there is no nothing. So it's only just the change in magnetic flux. The change in magnetic flux causes an induced current will set up in the conducting material, and that induced currents will form a circular. Induced currents will form at here in circular currents. So these circular currents, the electrons in that conducting material will form circular currents. So that circular currents develop a magnetic pole which opposes the motion of the magnet. So this is a very advantageous situation if we can take. So without any friction, we can control the motion, and if the magnet is out of the conducting material, so it's having its own natural motion. But when it is in with the conducting material, so it comes to rest all of a sudden. So this is a phenomena which we can use in the magnetic braking. So here object comes to rest by itself, and this rest, during this process there is no cause of extra friction. Let us try to observe the activities what we need to know about this eddy currents. So eddy currents are nothing but the currents which is developed in the thick conducting materials, and these currents are circular currents. So these eddy currents will always opposes the motion of the magnet. So let us observe the same. Suppose if you take a magnet, so that is the magnetic material, and if you take a conducting pendulum, so it's an a thick aluminum conducting pendulum, which I am going to hang right at there. So we are using different types of the conducting pendulums, how these eddy currents will affect. So further, if you take first a conducting pendulum which oscillates freely, and here you can see it's not having any gaps and all. Now if this conducting pendulum, its aluminum pendulum, is kept in the magnetic field, so here you can see the motion of that pendulum, it comes to rest. So that is due to because of the eddy currents which are developing in that material. Now if you can place another, if you can observe, here still damping is there, but the motion comes to rest. But if you can change, just like comb type, here you do observe, so it's just oscillating as without affecting the eddy currents. Now what causes this shape, and what causes of that comb shape? So if in this material the eddy currents are formed in circular pattern when it kept in the external magnetic field, so the change in magnetic flux, how it is changing? Because the pendulum wants to oscillate. So the change in magnetic flux causes an induced currents. So here induced currents are nothing but eddy currents. This eddy currents will form circular pattern. So this eddy currents will circular pattern, and this develop the opposing pole of the magnet. So that's the reason they will comes to rest. So the pendulum do not oscillate freely when it kept in an external magnetic field due to because of the presence of the eddy currents which they develop. But when you can take this comb shape, so here if you do observe at the bottom, so here it is a gap is present at there. So because of this gap, you see a noticeable gap is right at here. So because of this gap, so they do not form circular currents. So because it do not form the particular enter the closed path. And if you can do observe the magnetic moment equal to the product of current times area. So here the circular area is incomplete. So that's the reason it do not form eddy currents if you can take like this comb shape. So this will reduces the eddy currents. It do not show any effect of the eddy currents. So there won't be any damping in the presence of the magnetic field. Just it will oscillate. So these eddy currents are in this particular case is reduced. So if you take a rectangular slot that is made up of copper or aluminium, so because of the presence of the eddy currents, so there is damping of the pendulum. But if you take a slotted pendulum or a holes pendulum, so because of the holes, there is no electromagnetic damping which occurs. Then the plate swings very freely. So these are about the eddy currents, and the eddy currents will form a circular paths. So that's why these also called as circular currents. So these eddy currents are having both the positive effect and the negative effect. So when you can take to the applications of the eddy currents, so this can be used in the magnetic braking in the trains. So because they do not involve friction and there is no extra loss of energy while braking. So especially when bullet trains or magnetic trains which they move, so these are very useful in the as an advantage. And the second case, since the eddy currents is opposes the motion, or if you can call resistance to the motion, and it do not involve any kind of extra friction and any kind of extra loss of energy. So in that case we can use the electromagnetic damping. So certain galvanometers which are fixed with core non-magnetic materials. So to stop that, so we can generate an eddy currents in the core which opposes the motion to brings the magnet to the or the coil to the rest. So that is the one more advantages. And very main advantage is that eddy currents in the induction furnace. The induction furnace can be used to produce the high temperatures to prepare alloys. So to melt the consisting metals, if you can use a high frequency alternate current which is passes through coil, and because of the high frequency current, a strong magnetic field develops. If you can keep a material in that strong magnetic field, eddy currents will develop in that material. Because of the development of eddy currents in the material, what happens? The material gets hot. If the temperature is sufficient and more, then the material gets melt. So this is the known as induction furnace, the process which happens. Let's see one small demonstrations regarding the induction furnace. So this is a material which kept in a coil. So through the coil a strong alternate current which is passing. So the strong alternate current through this coil, an alternate current which is passing through the coil. So because of the alternating current passing, a strong magnetic field will develop. So if I can draw magnetic field, so this is the strong magnetic field will develop around the coil. Now because of this strong magnetic field, eddy currents will develop in this material. and that eddy currents will oppose the external magnetic field, so that causes the material is holding, and because of these eddy currents, so it generates a huge amount of heat. That heat causes to melt the material. So here the material is melting, so such a huge amount of heat is generating within the material because of the eddy currents which are developing in that material itself. So this is an advantage. We can use it as an induction furnace. So when such a temperature reaches, the material melts, then that is due to because only the presence of the eddy currents within the material. So how these eddy currents will stop the motion in the damping, and how these eddy currents are cause for the heat in the material. So that is due to because of the change in the magnetic flux through that conducting material. So if the change in magnetic flux through the conducting material causes a circular currents, so those circular currents develops an opposite pole, so which can oppose the motion of the magnetic material. So this circular currents is known as eddy currents. So eddy currents advantages in the induction furnace and electromagnetic braking, and in the to stop galvanometer coil. So these are about eddy currents.